Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today, we're going to tackle a practice problem set that relates to our lecture on spectroscopy. Let's go ahead and get started with problem number 1. Problem number 1 says, IR spectroscopy is most useful for distinguishing blank. IR spectroscopy is all about identifying specific types of bond vibrations based on the unique energies that molecules absorb in the infrared region. So the key idea here is that each type of bond vibrates at a different frequency depending on its strength and the atoms involved. With that in mind, let's break down the answer choices. A says double and triple bonds. This is in fact the correct answer. IR spectroscopy is very good at distinguishing between different types of bond orders. For example, a carbon-carbon double bond typically absorbs around 1650 wave numbers, while a carbon-carbon triple bond will absorb around 2200 wave numbers. So these are pretty distinct regions. And if you have a molecule and you want to know whether it contains a double or triple bond, IR would be a great tool to use. Now let's look at the other choices to confirm why they're wrong. B says carbon-hydrogen single bonds. While IR can in fact detect carbon-hydrogen stretches, this isn't very distinctive. That's because almost every organic molecule has carbon-hydrogen bonds. So they don't really help us differentiate between molecules in a meaningful way. Choice C says chirality of molecules. IR spectroscopy has no ability to detect chirality, or whether a molecule is even chiral or achiral. Finally, option D says relative percentage of enantiomers in mixtures. Again, this is not something IR can do. Enantiomers have identical IR spectra because they have the same functional groups and the same bond types. So you would need other techniques to assess this. So once again, the correct and the best answer is A, because IR is especially useful for distinguishing types of bonds, including double and triple bonds. Let's move on to problem 2. Problem 2 says oxygen does not exhibit an IR spectrum because blank. Let's walk through this. A says it has no molecular motions. That's not true. All molecules, even simple diatomic ones like oxygen gas, experience molecular motions, things like vibrations and rotations. In fact, the bond between the two oxygen atoms can stretch back and forth. So motion definitely exists, and that eliminates answer choice A. Option B says it is not possible to record IR spectra of a gaseous molecule. That's also incorrect. We routinely record IR spectra of gases, especially small ones like carbon dioxide. The physical state of the sample doesn't prevent us from collecting an IR spectrum. What matters is whether the molecule meets the conditions to absorb infrared light. So we can also eliminate B. C says molecular vibrations do not result in a change in the dipole moment. This is in fact the correct answer. This is a key rule in IR spectroscopy. For a bond vibration to absorb IR radiation, it must cause a change in the dipole moment of the molecule. That means there needs to be some kind of asymmetry, some uneven distribution of charge during the vibration. But oxygen gas, O2, it's made up of two identical atoms that are sharing electrons equally. So it's a non-polar molecule. So even though the bond stretches or compresses, there's no dipole moment to begin with and no change in dipole during vibration. So IR light can't be absorbed and the molecule stays IR inactive. Lastly, choice D talks about lone pairs. It says molecular oxygen contains 4 lone pairs overall. While it's true that each oxygen atom has lone pairs, this doesn't have anything to do with whether a molecule shows an IR spectrum. The presence of lone pairs isn't what determines IR activity. It's the dipole change during vibration that matters. So the best answer here is C. Oxygen doesn't absorb infrared radiation because its bond vibrations don't lead to a dipole moment change. Let's go ahead and move into problem 3 now. Problem 3 says, if IR spectroscopy was used to monitor the oxidation of benzyl alcohol to benzaldehyde, which of the following would provide the best evidence that the reaction was proceeding as planned? Before looking at the answer choices, let's think about what's happening in this reaction. We're starting with benzyl alcohol, which has a hydroxyl group, and we're converting it into benzaldehyde, which has a carbonyl group, a carbon that's double bonded to an oxygen. So if we're using IR to track this change, we should focus on what makes these two functional groups stand out. Now let's look at the answer choices. A says, comparing the fingerprint region of the spectra for the starting material and the product. Now, the fingerprint region is the region below 1500 wave numbers, and it's highly specific to each molecule. But the problem is, it's not very useful for tracking clear functional group changes, especially in something as simple as this oxidation. It's too messy and it's not specific enough for our goal. B says, noting the change in intensity of the peaks corresponding to the benzene ring. This is not correct because the aromatic ring stays exactly the same in both the starting material and the product. So we don't expect much change there. This is not going to help us monitor the progress of the reaction. C says, noting the appearance of a broad absorption peak in the region of 3100 to 3500 wave numbers. That region corresponds to OH stretches, which are found in alcohols. But remember, benzyl alcohol is the starting material. That means that the OH peak would be disappearing, not appearing. So this would have been relevant if we were forming an alcohol, but we're not. We're oxidizing one. So let's look at our final answer choice D. D says, noting the appearance of a strong absorption in the region of 1750 wave numbers. So this is going to be the correct answer. That's exactly where we would expect to see a carbonyl stretch, specifically a carbon-oxygen double bond. Carbonyls give a very strong, sharp signal in this region. And since aldehydes have a carbonyl group, its appearance in the IR spectrum would give us clear evidence that the alcohol has been converted into the aldehyde. So the correct answer for problem 3 is D. Problem 4 says, which of the following chemical shifts could correspond to an aldehyde proton signal in HNMR spectrum? Here we need to recall where aldehyde protons typically appear on an NMR spectrum. Aldehyde protons are quite de-shielded because they're directly attached to a carbon that's double bonded to an oxygen, this carbonyl group. And that carbonyl is very electron withdrawing, and it pulls electron density away from the hydrogen, which leaves it exposed to the magnetic field. As a result, this aldehyde proton shows up far downfield, usually around 9 to 10 ppm. Therefore, the correct answer is A. As a quick note here, choice C, 11 ppm, that's a little too far downfield. When we see signals around 11 to 12 ppm, that's usually associated with carboxylic acid protons, not aldehyde protons. So that is a bit too high. Once again, 4 is A. 5 says the isotope carbon-12 is not useful for NMR because blank. A says it is not abundant in nature. B says its resonances are not sensitive to the presence of neighboring atoms. C says it has no magnetic moment. And D says the signal to noise ratio in the spectrum is too low. So remember, for a nucleus to be NMR active, it needs to have a property called nuclear spin. Specifically, the nucleus must have a non-zero spin quantum number in order to interact with the magnetic field and absorb radio frequency radiation. Now, carbon-12, which is the most common isotope of carbon, actually has no nuclear spin. That means it has a spin quantum number of 0, and as a result, it doesn't produce a magnetic moment. If there's no magnetic moment, the nucleus won't interact with the magnetic field in an NMR experiment, and that means it can't absorb the energy required to show up in the spectrum. So the correct answer here is C. It has no magnetic moment, which is why it's not detectable by NMR. This is also why we use carbon-13, even though it's much less abundant. It's because it has a spin of 1/2, and it will produce a magnetic moment, so it can participate in NMR. Let's move on to problem 6. Problem 6 says in HNMR, splitting of spectral lines is due to blank. A says coupling between a carbon atom and protons attached to that carbon. B says coupling between a carbon atom and protons attached to adjacent carbon atoms. C says coupling between adjacent carbon atoms, and D says coupling between protons on adjacent carbon atoms. Let's talk about what actually causes splitting in proton NMR, or HNMR. When we look at a peak that appears as a doublet or triplet, so on, that's due to something called spin-spin coupling. This phenomenon happens when a proton is close enough to feel the influence of other protons nearby, specifically protons that are attached to adjacent carbon atoms. These neighboring protons generate tiny magnetic fields that slightly alter the magnetic environment experienced by the proton we're observing. Because of this, instead of seeing one smooth signal, the NMR detects several closely spaced signals, what we call splitting or multiplicity. So in summary, the splitting we see in proton NMR in its spectrum is caused by coupling between protons on adjacent carbon atoms. And that makes the correct answer for problem 6, answer choice D. Problem 7 says, compared to IR and NMR spectroscopy, UV or ultraviolet spectroscopy is preferred for detecting blank. A says aldehydes and ketones. B says unconjugated alkenes. C says conjugated alkenes. And D says aliphatic acids and amines. UV spectroscopy, it works by measuring how molecules absorb ultraviolet light, which causes electrons to get excited from a lower energy molecular orbital to a higher energy one. Now, for a molecule to absorb UV light, it needs to have pi electrons that can be promoted. And that's where conjugated systems come in. Conjugated alkenes are compounds that have alternating single and double bonds, which allow their pi electrons to become delocalized across the molecule. This delocalization lowers the energy gap between the highest occupied molecular orbital, this is what we call the HOMO, and the lowest unoccupied molecular orbital, or what we call LUMO. Because this gap is small, the energy from UV light is just right to promote an electron from the HOMO to the LUMO. That's why UV spectroscopy is especially good at detecting conjugated alkenes. They have the electronic structure that responds to UV light. On the other hand, things like aldehydes and ketones and unconjugated alkenes, they can absorb UV to some extent, but not nearly as strongly or predictably. And functional groups like aliphatic acids and amines, they don't absorb UV light in a meaningful way at all. So the best answer here is C, conjugated alkenes, because they're the compounds most effectively analyzed using UV spectroscopy out of our 4 answer choices. So 7 is C. Let's move on to problem 8. Problem 8 says, considering only the 0 to 4.5 ppm region of a proton NMR spectrum, how could ethanol and isopropanol be distinguished? The key here is to recognize the coupling patterns caused by hydrogens on adjacent carbon atoms, which show up clearly within this chemical shift range. First, let's think about ethanol. Ethanol has a methyl group, CH3, connected to a CH2 group that is then connected to our OH or hydroxyl group. Now, let's start by looking at our methyl group. In terms of splitting, the methyl group has 3 protons that are adjacent to the CH2 group, which contains 2 protons. So then, according to the N+1 rule, that methyl group will appear as a N+1, which is equal to 2 plus 1, which is equal to 3. It will appear as 3 peaks or a triplet because of those 2 neighbors. Now let's look at the methylene group here, CH2. It sits between the methyl group and the hydroxyl group. But proton exchange with OH usually causes that proton to not couple. So we're really just focused on the 3 protons on the methyl group next to it. That means that the methylene signal will appear as 3 plus 1, which is equal to 4. It will appear as 4 peaks or a quartet. So for ethanol, in the 0 to 4.5 ppm region, we're going to see a triplet and a quartet. Now let's look at isopropanol. Here we have 2 methyl groups on the ends here, CH3 and CH3, and in the middle we have a carbon that's bonded to a single hydrogen and to a hydroxyl group. This time, the 2 methyl groups are equivalent, and they each have 3 protons, and they're both adjacent to the same CH group. So each methyl group sees 1 proton next door, so that's 1 plus 1, and that gives us 2 peaks. So that gives rise to a doublet. Meanwhile, that central carbon that's bonded to just a single hydrogen, it has 6 equivalent protons from the 2 methyl groups as neighbors, which means that the splitting that this will have is N+1, which is equal to 6 plus 1. That gives rise to 7 peaks or a septet. So to recap, ethanol gives us a triplet and a quartet, while isopropanol gives us a doublet and a septet. And these patterns are going to fall within the 0 to 4.5 ppm region. That means that the correct answer for problem 8 is B. Problem 9 says, before absorbing an ultraviolet photon, electrons can be found in blank. Ultraviolet spectroscopy deals with electronic transitions, specifically electrons jumping from a lower energy orbital to a higher energy orbital. The most common transition we talk about is from the HOMO to the LUMO, and these are acronyms for the highest occupied molecular orbital and the lowest unoccupied molecular orbital, respectively. The key word here is occupied. The HOMO contains electrons because it's the highest energy orbital that still has electrons in it. The LUMO, on the other hand, is the next available energy level, but it's empty until the electron absorbs energy. So before any ultraviolet photon is absorbed, the electron hasn't moved yet. It's still sitting in the HOMO, waiting for that energy boost to jump it up to the LUMO. That's why the correct answer for problem 9 is A. Problem 10 says, in an IR spectrum, how does extended conjugation of double bonds affect the absorbance band of carbonyl stretches compared with normal absorption? A says the absorbance band will occur at a lower wave number. B says the absorbance band will occur at a higher wave number. C says the absorbance band will occur at the same wave number. And D says the absorbance band will disappear. Normally, when you see a carbonyl group, like a ketone or an aldehyde, it shows up as a very strong, sharp peak around 1700 wave number. That's the typical wave number for the stretching vibration of a carbon-oxygen double bond. But what happens when the carbonyl is conjugated to a double bond? Well, conjugation allows electrons to delocalize across the pi system. That means the electrons in the carbonyl bond aren't just staying between the carbon and oxygen. They're being shared across adjacent bonds too. This partial delocalization gives the carbon-oxygen bond more single bond character. And if a bond is weaker, it doesn't vibrate as fast and it stretches more slowly. So what does that mean in terms of IR? Well, a slower vibration corresponds to a lower energy. And in IR spectroscopy, lower energy means lower wave number. So instead of seeing that carbonyl stretch around 1700 to 1750 wave numbers, you might see it closer to 1680 wave numbers in a conjugated system. That's why the correct answer choice here is A. Problem 11 says, wave number is directly proportional to blank. A says wavelength, B says frequency, C says percent transmittance, and D says absorbance. In infrared spectroscopy, wave number is a way of expressing energy. It tells us how many wave cycles fit into 1 centimeter. The units are inverse centimeters. Now, wave number is mathematically equal to 1 divided by the wavelength. So right away, we know that wave number and wavelength are inversely related. That means if the wavelength gets longer, the wave number gets smaller. And if the wavelength gets shorter, then the wave number gets larger. So wave number is not directly proportional to wavelength. That eliminates answer choice A. Now let's think about frequency. Frequency and wave number These are directly related. When frequency increases, wave number increases too. And that's because both are tied to energy. Higher frequency means higher energy, and higher energy corresponds to a higher wave number on the IR spectrum. So wave number is directly proportional to frequency. What about percent transmittance and absorbance? These values tell us how much light gets through or is absorbed, but they don't tell us anything about the position of a peak in the spectrum. That means they don't affect wave number at all. So the correct answer here is B. Problem 12 says, 2 enantiomers will blink. A says have identical IR spectra because they have the same functional groups. B says have identical IR spectra because they have the same specific rotation. C says have different IR spectra because they are structurally different. And D says have different IR spectra because they have different specific rotations. Now, enantiomers are mirror images of each other. So they have the exact same atoms, bonds, and connectivity. That means they have the exact same functional groups, which are what IR spectroscopy detects. IR spectroscopy doesn't care about chirality. It just tells us which types of bonds are present and how they're vibrating. So even though enantiomers are non-superimposable mirror images, they have identical IR spectra because their bond types and their functional group environments are the same. So the correct answer is A. Now we can move into problem 13. And problem 13 says, in a molecule containing a carboxylic acid group, what would be expected in a proton NMR spectrum? A says a D-shielded hydrogen peak for the hydroxyl hydrogen shifted left. B says a D-shielded hydrogen peak for the hydroxyl hydrogen shifted right. C says a shielded hydrogen peak for the hydroxyl hydrogen shifted left. And D says a shielded hydrogen peak for the hydroxyl hydrogen shifted right. In a molecule that contains a carboxylic acid group, the hydrogen that's directly attached to the hydroxyl part of that carboxyl group is highly D-shielded. That's because the carboxylic acid functional group is very electronegative and it pulls electron density away from the hydrogen nucleus. When a proton is D-shielded, it feels more of the external magnetic field and it shows up downfield on the spectrum, which means it appears further to the left on the x-axis of the NMR spectrum. So if we're interpreting what kind of peak we expect, it's a D-shielded hydrogen peak that appears to the left. And that means 13 is A. Problem 14 says the coupling constant J is blank. A says the value of n+1 when determining splitting in NMR spectra. B says measured in parts per million. C says corrected for by calibration with TMS. And D says a measure of the degree of splitting caused by other atoms in the molecule. Now, the coupling constant, represented by the letter J, is a measure of how strongly two nuclear spins influence each other. Specifically, how much one proton affects the magnetic environment of a nearby proton through the chemical bonds between them. This interaction causes a signal to split into multiple peaks, and the coupling constant value tells us how wide that splitting is. It's measured in hertz, and a larger coupling constant value means that the peaks are spaced further apart. So rather than just telling us how many neighboring protons are causing the splitting, which is what the n+1 rule does, The coupling constant gives us a precise measurement of the strength of that interaction. That makes the correct answer D. It's a measure of the degree of splitting caused by other atoms in the molecule. Now we can move into our last and final problem. Problem 15 says, the IR spectrum of a fully protonated amino acid would likely contain which of the following peaks? Statement 1 says a sharp peak at 1750 wave numbers. 2 says a sharp peak at 3300 wave numbers. And statement 3 says a broad peak at 3300 wave numbers. To answer this one, let's walk through what kinds of bonds are present in a fully protonated amino acid and how they show up in an IR spectrum. Now, an amino acid is a carbon, a central carbon, that's bonded to a hydrogen atom, to an amino group, to a carboxyl group, and then to a side chain that we're going to write as R. Once again, this is a fully protonated amino acid. So that contains our carboxylic acid group, COOH, and a protonated amino group, so NH3, and it has a positive charge here. The carboxylic acid group, this is going to include a carbonyl bond, which gives a sharp peak around 1700 to 1750 wave numbers. So that confirms peak 1. That statement 1 is correct. Now let's think about the NH stretches. This group right here, it produces sharp NH stretches around 3300 wave numbers, which supports statement 2. But amino acids also contain a hydroxyl group from the carboxylic acid, and an OH bond typically produces broad peaks around 3300 wave numbers due to hydrogen bonding. That means statement 3 is also correct. So a fully protonated amino acid should show all 3 of these peaks, and that means that the correct answer is D. With that, we've completed this practice problem set. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.